Good morning to Dr. Chin Simi. Today, I would like to present about mini project for process simulation and computer-aided design. Before I proceed, let me introduce myself. My name is Putri Sabrina binti Muhammad Yusri, matric ID KA19209. We proceed with Chapter 1, Thermodynamic Model Selection. Okay, as you can see in this slide, I had attached Table 1, Physical Properties of Chemicals, which involved in this process. So, in order to determine the thermodynamic model selection, I used the Eric Carlson's recommendation. Okay, firstly, I determine whether there is a presence of polar or non-polar electrolyte compounds in this process. So, the pressure of this process used is less than 10 bars, and we do not have interaction parameters. Among the chemicals, most of the liquids are miscible. So in conclusion, we choose Unifect as thermodynamics model to stimulate the process in Expand Plus. Okay, we proceed to Chapter 2. Chapter 2 is Thermodynamic Binary Analysis. For Chapter 2, the Thermodynamic Binary Analysis, the main purpose of this is to obtain desired product with specific purity. The specific purity that we want is 99.9% of acrylic acid. Therefore, thermodynamic binary analysis is important in order to identify the presence of isotope in the system during the thermal separation. Okay, from all the binary analysis, there are several binary analysis. Only these two result isotope, which are acidic acid and water, and also acetic acid and water at atmospheric pressure. Chapter 3 is the process flow diagram. There are two feed which include air and propylene. Then it mix in mixer 1, then go to compressor, heater, reactor, heat exchanger, flash column, splitter, distillation column, another distillation column, and also vessel. Okay, this is the overall process flow diagram for our project. Okay, we proceed to Chapter 4. Chapter 4 is feed materials flow rate and products specification. Okay, according to the process flow diagram, you can see the feed streams for the process are air and propylene streams, while the product is stream number 9. From the table 3 in the slide, the production rate of acrylic acid is around 50,225.033 tons per operational year with the purity 99.88%. Air inlet flow rate is 1,150 kmol per hour, with propylene inlet flow rate is 109 kmol per hour, are required in order to achieve the desired acrylic acid production. Next is reactor modeling. This reactor modeling is stimulated using Aspen Plus. Okay, this is the screenshot I had captured from the Aspen. So first step is list all the components involved in the process. It has propylene, air, acrylic acid, water, acetylene, carbon dioxide, oxygen, and also nitrogen. Next, we put the method used in the process as I explained in Chapter 1. We had decided to use Unifect as the thermodynamic model. Next, we construct the main flow sheet referring to the process flow diagram for number 3. Next is the specification for reactor. So the specification for reactor that we use is operational year was set at 8,000 hours. Next is the feed material of air. For the feed material of air, first guess and estimation of the inlet air flow rate is 450 kmol per hour with 0.21 oxygen and 0.79 of nitrogen. For the feed material of propylene, the flow rate is assumed to be 45 kmol per hour for total flow rate and pressure 1 bar with temperature 25 degree. The mole fraction are only 1 for propylene. Next, step number 7 is specification for compressor. So the compressor type is isentropic with discharge pressure estimated as 250 kPa. For heater, the heater was set to the temperature of 310 degree with zero pressure drop. Valid phase was vapor phase. Next is specification for mixer. For mixer, 100 is assumed as also zero pressure drop with only vapor phase exists. For the reactor, specific reactor temperature was set at 310 degrees Celsius. The diameter of reactor used is 0.5 with initial gas of length as 1 meter. The valid phase in the reactor is vapor phase only. Then it continues with selection in reaction set R1, which happen in R100 in reaction step. At there, set the pressure of reactor is 250 kPa with zero pressure drops since isobaric reaction. We move to reaction 1 for reactor. There are 3 reactions with respective stoichiometry in configuration tab. For reaction 1, the coefficient of propylene is -1, oxygen -1.5, the products oxalic acid 1 and also water 1. Okay, for reaction 2 for reactor, the propylene coefficient is -1, oxygen is -2.5, acetylene is 1, carbon dioxide is 1, and water is 1. For reaction 3 of reactor, the propylene coefficient is -1, oxygen is -4.5. For the product, carbon dioxide is 3 and also water is 3. For all these 3 reactions, it is referring to the chemical reaction. We move to the kinetic of each reaction. So we had insert the value of K and also energy values respectively for each reaction. All the reacting phase is vapor with driving force of partial pressure in Kp. Okay, the orders of each reaction are same with first order of propylene and the first order to oxygen. The unit of E that we use is kilocalorie per kilomole, while reaction rate units is kilomole over meter cube dot hour. The kinetic model for reaction 1 is K value is 15,159,000. Energy is 15,000 kilocal per kilomole. For kinetic model for reaction 2, the value of K is 883000 and energy is 20,000 kilocal per kilomole. And for kinetic models for reaction 3, the value of K is 1.81 exponent 8 and energy is 25,000 kilocal per kilomole. Okay, we proceed with the driving force of process. The propylene was set exponent 1 and also oxygen is exponent 1. And then run the simulation. Then we will conduct sensitive analysis to determine the suitable reaction pressure to produce more oxalic acid. Okay, as you can see is the specification of the reactor. We add the new sensitive analysis, field pressure of R1 on 1 in Veritab, define outlet flow rate of acrylic acid and acetic acid in defined tab. Then all field variables are tabulated. Run again and get the sensitive analysis results as you can see in the slide. The result shows that increasing reactor pressure will increase outlet flow rate of acrylic acid. Thus, pressure of 250 kPa is valid to be used. Next is design spec is introduced to set the conversion of propylene as 0.9. The main purpose to set this conversion as there are 10% of gas bypassing and the maximum conversion in the reactor will become 0.9 only. In the design spec for the reactor, we will define inlet and outlet flow rate of propylene in R101. Then we fill the spec with formula of conversion, and the target is 0.9 with tolerance of 0.001. In Veritap, the length of reactor will vary in order to achieve the conversion. Deactivate R100 sensitivity first before run again the simulation, and from the result of design spec of reactor, in order to obtain conversion of 0.9, length of reactor should be 3.33 meter. We will proceed with the results of reactor. The target production rate of acrylic acid is 50,000 metric ton per year. So the mass flow rate of acrylic acid produced is 20,164.7 tons per operation year, as you can see in the slide from the simulation. In order to increase the mass flow rate of acrylic acid, we will change the inlet flow rate of air and propylene. Okay, for the feed material of air, we will change the total flow rate to 1,350 kmol per hour, and feed material of propylene to 135 kmol per hour respectively. For the configuration, we will go to the configuration tab in setup of R101, then check multi-tube reactor with number of tubes is 3, and then run the simulation again. Then from the final results in stream summary, the production of acrylic acid is more than 50,000 tons per year, which is around 60,494.2 tons per operational year. But it's okay since some parts of acrylic acid may lose during the separation process, so the production in reactor should be more than the targeted production. We move to chapter 6, purification process modeling. Prior to separation via distillation column, we must separate first liquid and vapor into different streams to further increase the efficiency of separation. In this process, the separation sequence starts with flash 2 column, which is V100. However, to make sure that the separation is effective, a cooler is added to reduce the temperature and pressure. So first is heat exchanger E101 used as a cooler. The temperature set is 10 degree and pressure is 100 kPa. Next, to separate acetic acid and oxalic acid from the output stream, flash 2 V100 was used, and the result was quite ideal with some water. Okay, for distillation column T100, we will first using shortcut distillation column, which use the STW to get all the optimum number of stages, refract ratio, and other unnecessary column operation parameters. So in this T100, water was being set as the light key with 99% recovery, and acrylic acid was being set as heavy key with 1% recovery in the distillate stream. The pressure of both condenser and boiler was set at 1 bar, with 30 number of stages assumed as initial gas. Then we will get the optimum number of stages, refract ratio, and other necessary column operation parameters to use in refract model. Okay, so for the refract model, we will use design spec to obtain the desired product specification and also a reasonable recovery. The number of feed stage is set as 17 above the stage under the stream step, and the condenser was set to a total condenser with refract ratio of 1.21843 and distillate to feed ratio of 0.608604 in the configuration tab. These two values were obtained from the STW from previous slide. Okay, the condenser pressure stage 1 also was set as 1 bar according to the top feed pressure. Okay, we move to distillation column T101. Okay, for this distillation column, insert a right frag block, which is T101, onto the flowsheet and connect the stream 7 as feed, while stream 8 is a distillate stream and stream 9 is a bottom stream. Okay, the condenser was set to total condenser with refractory ratio of 8.57354 and also distillate to feed ratio of 0.10339 in the configuration tab. This value also obtained from the results of the STW from Aspen. The number of feed stage is set as 18 above the stage under the stream tab. Then the condenser pressure stage 1 was set as 1 bar according to the top feed pressure. The simulation is run by clicking F5 and checking the results under T101 block at stream 9 to check the purity of acrylic acid. So I had run the simulation, and in order to reach the mass purity of 99.9%, I decided to carry out the design spec function, and this design and vary function is conducted under T101 by design the mass purity and vary the block specification, reflux ratio, or distillate to feed ratio. Okay, we continue with design specification T101. The mass purity of acrylic acid is set as 0.999 in specification tab under column T101. Then all the components, the selected component is acrylic acid, and also the selected component is all the components except air. Okay, next is stream 9 is selected as our main acrylic acid, which will produce in S9. For the T101 specification vary, I used the value of distillate to feed ratio, which is lower bound 0.01 and upper bound is 0.99. Okay, so the result that I get by running the simulation, we are able to obtain 99.98% of acrylic acid in our product stream S9. Okay, we move to chapter 7, which involve overall process simulation without recycling. Okay, to achieve 50,000 metric tons capacity of acrylic acid, we have to set a sensitivity by using model analysis tools. So the inlet flow rate is validated by using a model analysis tool, which can reach the final production of 50,000 metric tons per year. Then after we set a sensitivity, we will change the inlet flow rate in propylene and also in air to make sure that the product capacity of 50,000 metric ton can be achieved. We set the sensitivity analysis in verify by variable the mole flow. Start point is 1215 and end point 1220. Okay, for the defined setting in sensitivity analysis, the mass flow rate outlet of acrylic acid were used. Okay, according to the sensitivity analysis of T101 result, we selected the inlet flow rate as 1219 kmol per hour and propylene inlet flow rate as 120.6 kmol per hour in order to achieve 99.98% of acrylic acid in product of stream 9. Then, by using the sensitivity and design spec function, the desired purity of acrylic acid is achieved as requested, and also the production of acrylic acid is 49,965.3 tons per operation year, which is fulfill the production rate required. Okay, I also tabulated the heat duty for unit operation in the non-recycling design, which the total energy consumption is negative 27,654.138 kilowatt. Okay, we continue with last chapter, chapter 8, overall process simulation with recycling. In this overall process with recycling, we add splitter, which split the fraction of the components, which are 0.9% of propylene, and acrylic acid as shown in the slide. Okay, similar to chapter 7, after adding the recycle stream, we also need to adjust the inlet flow rate in propylene and air in order to ensure the product capacity can be achieved. Okay, we use sensitivity analysis. We vary variable settings, the defined setting, and the sensitivity analysis result shows the status okay. So we decided to select the air inlet flow rate as 1150 kmol per hour and propylene inlet flow rate as 109 kmol per hour. Okay, according to the stream summary with recycling, I can conclude that the flow rate of propylene and air for recycled streams are being decreased from 120.6 kmol per hour and 1219 kmol per hour to 109 kmol per hour and 1150 kmol per hour respectively. This is because there is an extra recycle stream from flash column. So the total flow rate for 3 streams that enter mixer must not exceed the total flow rate for process without recycle, as the final productions of acrylic acid is exactly same for both cases. The recycled product from stream 3 will decrease the inlet flow rate of feed materials. In terms of the purity, both of recycle and non-recycle achieve a same value. As you can see in this slide, the mass purity that I get for the recycling stream is 99.88% of acrylic acid. Lastly is the heat duty for unit operation for recycling unit and comparison with without recycling unit. The total energy consumption for heat duty with recycle is negative 27,463.2046, while heat duty without recycle is negative 27,654.128. Okay, as a conclusion, the process without recycle stream has lower energy consumption than process with recycle stream. The higher the energy consumption, the cost of utilities is higher, as well as the electricity in the process plant. However, presence of recycle stream can be reduced the inlet flow rate of feed materials and also reduce the cost of purchasing raw feed materials as well as the production of waste. Commonly, extra cost on waste treatment is needed to be considered in plant operation when there is a presence of waste from the process production. I think that's all from me. Thank you.